Let's continue on the last part of the course on properties of materials. So, can you guess now what is the last property that we are going to learn? It's magnetic materials. Magnetic moments originate on atomic scale from the orbit and spin of electrons. These effects are also influenced by the particular electronic configuration of the different elements. I hope you still remember how to draw electronic configuration for each element. Electrons in matter have two contributing properties. We have spin and orbit. In material, the largest magnetic effects are due to the spin of electrons rather than orbit moments. The orbital moments play important part as well, but when there are uncompensated spins present in a molecule, the orbital contribution becomes negligible. What is magnetic dipole moment? Magnetic dipole moment is a torque material experience when exposed into a magnetic field. If you put an object in a magnetic field and it does not show any effect, it doesn't have this magnetic dipole moment. Let's say we take a bar magnet like this, and how do you know whether it is magnetized? How can we figure out? We can use compass with a small floating magnet on a needle. Let's say the red one is North Pole and the blue one is the South Pole. Put a compass on each side of the bar magnet and we can then see the south side of the magnet is pointing to the north of the bar magnet and the north part of the magnet in the compass is pointing to the south part of the bar magnet. Alright, so this is definitely magnetized and it is the magnetic dipole moment inside the bar is making it magnetized. But what happens when we break the bar magnet into half? So the north is still at this end and the south is on the other end. Now we have to test it again in the same way. So now we just created two dipoles. We can just keep on breaking it to get smaller magnets. So there is something intrinsic in the magnet causing it to be magnetized, and this is magnetic dipole moment. This is the transitions metal. So we have scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. So we can see zinc is complete orbital, but from scandium to copper, they have the unpaired electron. And this is how to draw the electronic configuration of different elements. Next, we have spontaneous magnetization. So we have ferromagnetic, we have antiferromagnetic, AFM, and we also have ferrimagnetic. Alright, a paramagnetic material has an unordered magnetic structure which fluctuates in time, averaging over time yields no permanent magnetization. So this is ferromagnetic, which we will learn in more detail as we go on. This is antiferromagnetic. The spin of electron align in regular pattern with neighboring spins pointing in opposite direction. Can you see that? One is pointing upward and the yellow orange one is pointing downwards. Then we also have ferrimagnetic. Ferrimagnetic is actually similar to antiferromagnetic, AFM, but opposing moments are unequal and spontaneous magnetization remains. This normally occurs when the population consists of different materials or ions such as a mix of Fe2 plus and Fe3 plus in the structure. Then here we have different elements. We have transition metals and rare earth at different temperature. They behave as ferromagnetic, or it can also behave as paramagnetic. So it depends on the temperature. Next, we have ferromagnetism. Ferromagnetism is a special case of paramagnet or paramagnetism in which the individual spin magnetic moments interact where the moments are coupled. The uncompensated spin in individual atoms of ferromagnetic material may couple either directly or intermediate anion, usually oxygen, and this forms super exchange. So we have direct exchange and super exchange in ferromagnetism. In crystal of a ferromagnetic material, this gives rise to a net magnetic moment due to coupling of spins in a preferred orientation. Keep in mind that this coupling of spins is quantum mechanical in nature and not purely due to magnetic force acting between neighboring atoms. As with paramagnets, ferromagnets have strong positive magnetic susceptibility. So magnetic susceptibility is actually a measure on how much a material can be magnetized when applied magnetic field, right? So unlike paramagnets, when the applied field is removed, they retain a component of magnetization in the direction of the applied field. They are permanently magnetized. They do have hysteresis. Also, their susceptibility is not dependent upon temperature in a way that follows Curie law. Temperature dependence of ferromagnetism. Since ferromagnetism results from the interaction of atomic moments in materials, there is an exchange energy associated with coupling the spin moments. At room temperature, the exchange energy is much greater than the energy due to randomizing thermal effects. If thermal effect exceeds the spin coupling exchange energy, the coupling breaks down and the material behaves as a paramagnet. This temperature is dependent on the material and is called Curie temperature, or in the case of antiferromagnetism, AFM, it's called Néel temperature. This is the typical curve for paramagnet and ferromagnet at different Curie temperature. Next, we have exchange and the Curie temperature. So start with a paramagnet. Suppose there is some local interaction going on that behave like a local magnetic field, and this from the exchange field. Don't worry about this. You just need to know that different material have different Curie temperature. Although the most common example of magnetic materials that we know is iron. But there's not only iron that can be magnetized, there's also other materials such as cobalt, nickel, and so on. You can see the long list here. They all have different Curie temperature. This is the hysteresis loop. We have seen this earlier. So in hysteresis loop, we have magnetization of material versus applied magnetic field. So the hysteresis loop shows the history-dependent nature of magnetization of a ferromagnetic materials. So once the material has been driven saturation, the magnetizing field can then be dropped to zero, and the material will retain most of its magnetization. It remembers, so that's why it can be used as magnetic memory device. So you need to know how to plot this hysteresis loop. So magnetization of material versus applied magnetic field intensity, H, M versus H. And this is the typical shape of the hysteresis loop. So there are 4 important points here. 1, 2, 3, and 4. Okay, so at this point, the material follows a nonlinear magnetization curve when magnetized from zero field value. So at this point, material magnetized to saturation by alignment of domains. You can see all the domains are aligned towards the right. Okay, they're all in the same direction. Then, when driving magnetic field drops to zero, Right here, magnetization is 0. The ferromagnetic material retains a considerable degree of magnetization. This is useful as magnetic memory device. So this is how it looks like, the domains. Okay, and then it drops further here, where the driving magnetic field must be reversed and increased to a large value to drive the magnetization to 0 again. Okay, so this is how it looks like. Then towards saturation in the opposite direction here, okay, you can see this direction is totally opposite of this one. Okay, so that is the properties of hysteresis in magnetic material that you have to know. Okay, that's it for ferromagnetic material. Then we have ferrimagnetics and antiferromagnetism. Ions in most ferrimagnets and antiferromagnets are positioned on two sublattices such that the spin on each sublattice tend to be aligned with each other, but spins on different sublattices tend to be oriented in opposite directions. The lattice sites come in two flavors. We have tetrahedral site and octahedral site. For tetrahedral, the iron is surrounded by 4 oxygen ions, and for octahedral site, the iron is surrounded by 6 oxygen ions. Okay, don't worry about this. You just need to have the idea that the lattice sites can be either in tetrahedral or octahedral site. And this is the typical curve for antiferromagnets. And lastly, you need to know some example of antiferromagnets materials such as chromium, manganese, Cr2O3, cobalt oxide, and Fe2O3. Alright, so we have actually come to the end of the course. I hope you have enjoyed the course and learned as much as possible. And thank you for watching.